So right, so maybe we can start. So our next speaker is Philippe Corboz from Amsterdam, and we're talking about the two-dimensional Hubbard model and simulations with infinite maps.
Thanks. Okay, thank you very much. Let me also thank the organizers for the invitation. I think it's really great to have such a workshop which brings together people from various backgrounds to discuss about tensor networks. So my background is computational condensed matter physics. I'm mostly focusing on developing and also applying 2D tensor networks to condensed matter problems. And today I would like to tell you a bit about our progress in simulating the 2D Hubbard model, which, as you probably know, is a very simple model of interacting electrons, and it's believed to be relevant for high TC superconductivity, but it has been notoriously difficult to study it for several decades. And the approach I'm focusing on is iPEPS, or infinite PEPS, which is a 2D tensor network ansatz to represent a wave function directly in the thermodynamic limit. Okay, so since I have an hour, this is not going to be the only topic, so I will also tell you a bit about other progress we made with this approach. So here's the outline of the talk. So the first thing I will start with is to tell you about a joint work with the Simon's collaboration on the many electron problem, which involves many different groups, which are experts in different computational methods. So let me just acknowledge them here. That's Bo Xiaosheng, Xiaomin Chung, Georg Ehlers, Ming-Pu Qin, Reinhard Noack, Hao Shi, Steve White, Shiwei Zhang, and Carlo Chan. And the goal of this collaboration was to focus on one particularly challenging point in the phase diagram of the 2D Hubbard model, so U over T equals 8 and 1/8 doping. And then by pushing several state-of-the-art methods to their current limits, try to get a conclusive answer what the ground state is at this challenging point in the phase diagram. So besides iPEPS, we also used DMRG, auxiliary field quantum Monte Carlo, and the density matrix embedding theory. And I will show you that indeed this was possible here to get a conclusive answer, namely that the ground state is a so-called stripe state. So that's a state where the charges and the spin density is modulated in a certain direction. Okay, and then I will also tell you about a more recent work where we extended these calculations to an extended Hubbard model, where we include an additional next nearest neighbor hopping term, which is also known to be present in effective models of high TC superconductors. And what we found here is a shift from a period 8 stripe down to a period 4 stripe, and that's in the end also the typical stripe here, which is observed in experiments. So that's joint work together with Simon Chung and Boris Ponsoon from my group. Then in the second part, I would like to switch topic and tell you about an approach called the finite correlation length scaling with iPEPS, which is a method to systematically study continuous quantum phase transitions. So it works in a very similar spirit as conventional finite size scaling, but instead of doing the scaling analysis in terms of different system sizes, we do it in terms of an effective correlation length that we extract from our iPEPS simulations. And then it works in a very similar way, so we can, in a systematic way, extract critical couplings and critical exponents. So that's work together with Piotr Czarnik, Geert Kapteins, and Luca Talekotzo, who was of course here this week but had to leave this morning. And then in the very end, I would like to also tell you about some other directions, only very briefly, so about the SUN Hubbard model, and then also iPEPS simulations at finite temperature. Okay, but let's start with the 2D Hubbard model, so which can really be seen as the most basic model of strongly correlated electrons. So it plays a bit a similar role in the field of strongly correlated electrons as the Ising model in classical static. Right? So you just have a Hamiltonian with a nearest neighbor hopping term, so just hopping between nearest neighbors, and then an on-site repulsion with repulsion strength U. So already more than 30 years ago, it was suggested that this model is the relevant model for high TC superconductivity of the cuprates. So high TC is still not fully understood, so you can imagine there has been an enormous interest in solving this model accurately. However, despite a lot of effort and despite its simplicity, it has not been conclusively solved yet, and there's still no consensus about this question, so whether it's really the relevant model, and also the entire phase diagram is still not known. And of course, the main reason why it's so challenging is because that's really a typical model which strongly suffers from the negative sign problem, so you can't really use just conventional quantum Monte Carlo to study this problem. But still, there has been quite an impressive progress with many other methods that have been developed for strongly correlated electron systems. So there's a long list of different approaches, and all these methods have their own advantages and disadvantages. So there exists still no magic black box method which could just solve you everything that you want. But still, as all these methods become more and more accurate, the hope is that at some point they will start giving conclusive results rather than contradicting each other. And that in the end was the motivation to do such a joint study of the 2D Hubbard model and see if we really take several methods and push them if we can get a conclusive answer. Now, there have been many predictions what the ground state phases of the 2D Hubbard model are, and I will focus here on the main candidates in the strongly correlated regime, so U over T around 8, which is a typical value relevant for the cuprates, and then 1/8 doping. And there also have been many predictions for the TJ model, which is an effective model of the 2D Hubbard model. So the most basic question is, let's go to 0 doping, where we know that the system is just an antiferromagnet, so 0 doping means 1 electron per site, and the physics here is well understood. In this case, there's also no sign problem, so we know it very well. But then the question is, what happens if we start doping the system with holes? Right? So if you take away some of the electrons, what do these holes do, and what kind of states do we obtain in this case? Now, the two main candidates, or the two main scenarios, is that these holes delocalize in a uniform way, giving rise to a uniform D-wave superconducting state on the one hand, and another possibility is that these holes form such domain walls here, which separate antiferromagnetic regions in between them, and these are called stripes. So in such a stripe here, you have a modulation of the hole and spin density. And both these states were also observed in various families of the cuprates. Now there's a long history on the theory of the stripes, which I will not go into the details. So initially stripes were found to be insulating, but then later it was found that stripes can actually also coexist with the superconductivity. Now from a numerics point of view, there exist many works which predicted this uniform D-wave state, and many other works which were in favor of the stripe state. And then some of the works also predicted both states, but then extremely close in energy, right? So in the end, we can really say this question, which of the two is the true ground state here, has been really an open problem for a very long time. And in the end, this was our goal, to get a conclusive answer here, focusing on one particular point here in the phase diagram and trying to get an answer here using a combination of methods. I'm going to show you here, as I mentioned before, that the ground state is a stripe state. Okay, but before I come to the results, let me switch now to some brief introduction to iPEPS. So we already heard a very nice introduction also by Ignacio earlier this week. So I will really skip the basics and just tell you about the most important ingredients here. So everyone knows what a matrix product state is. And one thing I would like to point out is that many people also use matrix product states to study systems in 2 dimensions by putting it on a 2-dimensional lattice here with such a snake structure. So that in the end boils down in mapping your 2-dimensional model onto a 1-dimensional system with long-range interactions, right? So one can do that. However, the problem is that because this ansatz here does not reproduce an area along 2 dimensions, there is an involved computational cost which scales exponentially with this linear length here, right? So one can still do it, and many groups have obtained very nice results using this approach. So like Frank Polman or Steve White. So it's very powerful. It just means that you're limited in this direction, and for that reason, people typically consider long cylinders. So this is long, and then this direction here is then short. And short, in the case of the 2D Hubbard model, means that a typical length of 6. So this is what's feasible for the 2D Hubbard model. Okay, and in the end, 2-dimensional tensor networks have been developed in order to overcome this exponential scaling, and then the most general, most natural generalization of a matrix product state is a PEPS. Right? So we have also exactly 1 tensor per lattice side, but now on the 2-dimensional lattice where each tensor is connected to its nearest neighbor. Right? And in this approach, we then have a computational cost which scales polynomially with the system size and 1 dimension. Okay, now what we typically use in our calculations is infinite PEPS. So with an infinite PEPS, you can directly represent a wave function in the thermodynamic limit, and then the advantage is that you don't have a finite size and boundary effects. Right? And if your state is translation invariant, you can simply parameterize it by 1 tensor A here, which is repeated on your lattice. But since you're working in the thermodynamic limit, symmetries can also be spontaneously broken, and that's why we often need a certain unit cell of tensors which you repeat on the lattice. So think of a nil state, for example, with 2 sublattices. In that case, we would use an ansatz with 2 tensors A and B. Or more generally, what we use is a certain unit cell, so that would be a 4 times 2 unit cell, which is repeated. Right? So that's the type of ansatz we use. And then, depending on what unit cell size you use, you can represent different states. So it's in the end also a way to stabilize different candidate ground states. But in the end of the day, what you need to do is then to systematically compare the variational energies to see which of these candidate states is the true ground state. Right? So this is what we do in practice. So we start from our ansatz, which we know is a variational ansatz, and then we have to do an optimization of the tensors.
Sorry,
now,
Philippe,
yes?
Can you make sure that with this cell ansatz you are not missing a cell that actually would give a smaller energy?
So typically you would start with a small cell and then increase it and then see what happens. And then imagine you have a state with a strange period. You would see that the period, that the period actually depends on the cell size that you use. So there's a way to kind of systematically check what happens if you go to larger and larger cells, and then you might see that the period might lie somewhere in between. So in principle, that's possible, and of course you can never be 100% sure, but typically by testing many different cells, you can get quite a good idea. Okay, so once we start from a certain ansatz, of course, the next step is to actually find the parameters in the tensors. So I will not go into the details here, but we have different approaches for iPEPS. So there's families of approaches based on imaginary time evolution, but we can also do a direct energy minimization. So there's advantages and disadvantages with both approaches, but I will not go too much into the details here. And then finally, once you have found your best state, you want to compute then quantities of interest. Right? And in matrix product state, this is simple because we can contract everything in an exact way. However, with PEPS and iPEPS, the contraction, if you want to do it exactly, is exponentially hard. So we need some approximate methods to do the contraction. Okay, so imagine you want to contract this two-dimensional, infinite two-dimensional tensor network. So that's already bra and ket layer put together. Right? So you have a square lattice. We heard already this week about TRG, which is one approach to contract such a network. What we typically use is the coordinate transfer matrix method. Let me just briefly sketch it. So imagine you want to compute something here on this side A here, And we can use this corner transfer matrix method to contract everything surrounding this middle tensor A here. So the approach gives us then some environment tensor, so consisting of this corner tensor C1 and an edge T1 and so on. So this C1 takes into account this upper left infinite corner of the infinite system, and the T1 takes into account such a half a column, infinite half column, and so on. Right, so that's the idea. And then the accuracy of this approximate contraction can be controlled by another bond dimension, which we typically call chi here. And then typically we'll make sure that things are converged as a function of this chi parameter.
But in this Ishino paper, this was done for classical. So
this was done for classical problems initially, exactly, back in the 90s. So let me just briefly sketch the way we do it here, which is a directional CTM approach, where the idea is that you start from a small system, and then you let the system grow in all directions, and you reiterate until you reach convergence. So let's start from the small system here, where we take some initial guess for the boundary. And then the first step, what I'm showing you now, is how we can let the system grow on the left side. And for that, we first introduce a new copy here of a column. So just a copy of T1A and T3. And then we multiply these tensors onto the left boundary. So this gives us a new tensor C1 tilde, T4 tilde, and C4 tilde. So a new boundary, but now with an enlarged bond dimension here. And then the last step is then the renormalization step, where we truncate this down to chi again. And then we have new tensors C1 tilde, T4 tilde, and C4 tilde, which have absorbed an additional row in the system. Right? So that's a left move. And then very similarly, we can do a right move to grow the system on the right, then top and down. And then this is reiterated until we have reached convergence. And then we can compute things in the middle here, which corresponds then to a value in the thermodynamic limit. And so this approach can also be easily generalized if you have larger unit cells of tensors without increasing the leading computational cost. So I will not go into the details how you can do this normalization step. There's different variants, but if anyone's interested, can always discuss later. So just a side remark in the end, if you want to compute, simulate the 2D Hubbard model, we need a fermionic tensor network ansatz. So we have to find a way how we can include fermionic anti-commutation rules in our ansatz. And now this has been worked out by many groups. Now it's 10 years ago. I will not go into the details. In the end, it's, let's say, a matter of bookkeeping of these minus signs here. And there exist different formulations, but in the end of the day, these formulations all describe the same fermionic tensor network ansatz. So also here, if anyone is interested, I can also explain more later. Okay, so this was about iPEPS. I will not go into the details of the other methods that we have used for the 2D Hubbard model. I only show you here an overview of the methods with their advantages and disadvantages, right? So first DMRG, you already know. So it's very accurate for cylinders up to a certain width. So here we have width 6. However, in the end, there remains an error due to this finite width, right? So with these widths, you can't really extrapolate to the thermodynamic limit. Now, iPEPS has no finite size effects, and you obtain a systematic improvement as you increase the bond dimension. But typically, we don't reach convergence in challenging problems. So in the end of the day, we have to extrapolate. So we'll come back to this later. Then DMET, or density matrix embedding theory. So it's a wave function-based cluster embedding technique. So where the idea is that you map your lattice problem onto a cluster impurity problem, which can be solved in a self-consistent way. So this approach has essentially no finite size effects, but there is a systematic error due to the size of the cluster you choose that you embed. So a bit similar as in cluster DMFT. And then the last one is auxiliary field quantum Monte Carlo. So this is exact at half filling. However, if you go away from half filling, there's a sign problem. And if you still want to do simulations, you can do this by using this so-called constrained path approximation, which, however, relies on a good choice of a trial wave function. So there's a systematic error depending on the choice of this trial wave function. Okay, so you see in the end, each of the methods has really some disadvantages, so it's going to be interesting to see how they actually compare. Okay, so let me now show you some of the iPEPS results. And first, for an ansatz just with two tensors A and B, if we take this ansatz, we can reproduce the uniform D-wave superconducting state. And what I show you here in this picture are the local observables measured in this unit cell here. Right? So these green disks here show you the local hole density. So you see it's the same on each side, so it's uniform. And then the arrows is the antiferromagnetic order. And then you also see the colored bonds here, which show you the amplitude of the nearest neighbor singlet pair. And there are different signs in X and Y direction, which is typical for D-wave pairing. Okay, so that's a superconducting state. And now we can also obtain the stripe state by taking a larger unit cell. So that would be an example of a paired 5 stripe obtained in a 5×2 unit cell. And now you see how the hole density is modulated in X direction. And also the spin density is modulated. And there's this typical pi phase shift in the antiferromagnetic order here, which makes it possible that this hole here can fluctuate back and forth without actually frustrating the antiferromagnetic order. That's why it's energetically a good state. So that's a paired 5 stripe, which also has coexisting superconductivity, as you see here. And then we can also obtain other stripes, so that's a paired 8 stripe. And what's special about this one is that it has exactly one hole per unit length, and in that case, superconductivity is entirely suppressed. There's other candidate ground states like this diagonal stripe state, as shown here, so where everything is modulated along the diagonal. So these are the candidate ground states. And now if you want to find out which of these is the true ground state, we have to systematically compare the energy, right? So I'll come back to this in a minute. Let me just briefly show you here also some earlier benchmarks. I want to highlight 2 things here. So here I'll show you a benchmark comparison at half filling. At half filling, there's no sign problem, so we can actually compare with quantum Monte Carlo. So that's the energy percent. The red points here are obtained from quantum Monte Carlo, so as a function of 1 over the system size. And here's the iPEPS data. Right? So you see how the variational energy improves as you increase the bond dimensions. And the dashed line is the extrapolated quantum Monte Carlo result to the thermodynamic limit. Right? So we are here already very close. Even without extrapolating, we obtain the ground state energy pretty accurately. And you see we're actually similarly far away from the thermodynamic limit as the last quantum Monte Carlo point here. The dot case is more challenging, of course. So here I would like to show you a comparison with a variational calculation here. So that's the previously best variational energy obtained from variational Monte Carlo combined with fixed node Monte Carlo plus 2 Lanczos steps. So it's kind of a combination of methods to obtain a low variational energy. But then you can clearly see that we can reach large bond dimensions that we can actually get below these previous state-of-the-art results. So meaning that as a variational approach, we are really very competitive with iPEPS to get very low variational energies. The other thing I would like to highlight here is, so that's previous data, and previously it has always been difficult to determine, so which of these 2 states, so uniform and stripe state, is actually lower, because it's not so clear how should we best extrapolate this data to the infinite limit. And often, if you try that, it actually does not give you a very accurate result. Let me show you one example to illustrate this, how tricky this is. Yes?
These plots, when you say iPEPS, you mean the combination of all the methods that you pointed out, or which particular update scheme you're using?
So here, this is full update calculation.
So just PEPS.
Yes,
just PEPS full update.
This is PEPS full update. Yes. Okay, so here I show you an example of an exactly solvable model. So just to have here the exact solution in green here, so the details don't matter too much. But here I show you the iPEPS data as a function of 1/d. So you see it goes down again, but then it seems difficult to extrapolate this data to the exact infinite D limit, right? So it's hardly visible. So this point is a variational bound, so it's an upper bound. And then typically the linear extrapolation here gives you a lower bound, but you see the error bar here is very large, right? So this is not very good. But the idea is now that you can improve this by plotting the data as a function of another quantity, namely a truncation error. So that's something which is often done in DMRG calculations as well. And here we have tried to do something similar with iPEPS, but also in the context of an imaginary time evolution algorithm. So I will not go into the details. So in the end, this W here, so the truncation error in the end tells you something about the degree of approximation in your wave function. And if you plot the data as a function of this W here, then we can extrapolate things much more accurately to the infinite limit. So that's the type of extrapolation we have used for the 2D Hubbard model. Okay, so here I show you a first comparison between two of the competing states. So again, the energy now as a function of the truncation error, here of this vertical period 5 stripe, the blue one, and the diagonal stripe. And then if you take the extrapolation, we find that this vertical stripe is lower in the infinity limit, right? And now we can try to do the same thing between the stripe and the uniform state. So the uniform state here, the black triangles, and if we take the extrapolation, we clearly find that the stripe is lower than the uniform state, right? Which in the end is the answer to this long-standing question we had at the beginning.
One question, so this diagonal, you take the diagonal orbit, you have a side of your stripe which is very big. Wouldn't it
unit cell, yes.
Unit cell. So wouldn't it include already the stripe itself? So shouldn't you need energy get the stripe?
So the unit cell of the diagonal stripe was actually not a rectangular one, but you know, with the vectors going onto the diagonal. So it's
not this equal.
Exactly, exactly right. So
it's not the general that you take up.
No, in that case we restricted it. So it typically was run, you know, without conditions. But then if you want to particularly look at this particular state, then we can impose actually the structure in the unit cell. Yes.
Sorry, Philippe, this bus you associate with an error of the extrapolation?
Yes, yes. So that's the extrapolation error bar. Yes.
Then what is the significance of this statement?
It's so these are 1 sigma error bars. So okay. So in the end, we can also move on now and then compare the energies of different stripe periods, right? So here I show you data, example data for period 5, 7, and 8. And then you see that the competition here is even stronger, right? So they're all very close in energy. There seems to be a slight tendency for the period 8 stripe, but in the end, they're really close. So this is really tricky to determine, right? So slight tendency for period 8 maybe, but in the end, they're very close. So let me now show you a comparison with the other methods. So first this plot here, so that's the energy difference with respect to the lowest energy state, which is a stripe state. And here's the DMT result for the uniform D wave state. And you see the distance to the stripe state is similar as the iPEPS result, so around 0.01 T. And then in this other plot, I show you the energy difference as a function of the stripe period. And then what we find is that all the methods predict a very strong competition between periods 5 and 8. So we have here many data which lies very close to each other. There is a slight tendency for period 8 stripe. And in the end, again, so we have this very close competition.
Is it possible to understand this coincidence in terms of the symmetry of the?
It would be interesting to yes. It's not, let's say it's not entirely clear, but it's also one of the scenarios that you have, you know, a state of fluctuating stripes, which with not a fixed period, but actually where stripes can fluctuate freely, right? And that's also in the end would be compatible, at least with the resolution you have now. That would also be compatible with such a scenario here. But at this point, that's difficult to tell. Okay, and here I show you a comparison of the actual energy of the period 8 stripe obtained from all the methods. Right, so these error bars in the end are not true error bars because all these methods have their own systematic error. So it's just an error bar computed, for example, here from the Monte Carlo sampling, but it's not including systematic error. But in the end, it's actually nice to see that the range of energies is actually pretty close with all these methods, right? So if you compare that to results from 5 or 10 years ago, that's really an order of magnitude better. Then we can also...
But then the computational effort, where is the biggest, or is it comparable?
Yeah, that would be interesting, yeah?
Because if they give the same result, what should they take?
Oh no, but you see, so the goal here was not to find out which of the methods is really the best one, but somehow to try to, I think in the end, for a challenging problem as the Hubbard model, it's actually good to try to nail it down coming from different different angles, exactly. So it was not the goal to actually.
No, I know.
So that's of course that's something to discuss as well. But in the end, I think I really see it as complementary in the end, right? So
are all the methods kind of variational?
No. So this is not variational. This is not variational. So it's only here. But DMRG is in the sense that's so for a finite system size. So it's not variational for the thermodynamic limit. So in the end, it's you can't say the lowest is best. Yeah.
So you mean that this DMAT is kind of self-consistent?
Yes, it's self-consistent, but it's not variational. Yeah. So we can also compare orders of all these stripes, and then in the end you see the magnitudes varies quite a bit from method to method, but still the qualitative features of the stripes are similar if you compare these different approaches. Now, one, let's say, issue of this data is that the typical stripe period observed in experiments is a period 4, and the period 4 stripe is clearly higher in energy than these other periods here. Right? And the question is then, can we get another period if we move towards a more realistic model of the cube rates? And to get more insights into this, we started looking at the extended 2D Hubbard model. So we add an additional next nearest neighbor hopping, which is also known to be quite large if you look at effective models of high TC superconductors. So that's, I show you here data which was obtained by Boris Ponsoon and Simon Chun from our group. So that's for U over T equals 10 at 1/8 doping. And then the nice thing that we see here is that as we increase the negative T prime over T, there's actually a big area where period 4 stripes get stabilized, right? So we have a shift from large periods to smaller periods, and then we're in an extended region here where period 4 stripes are stable. What's also interesting to see, so that's around here, that's the kind of realistic regime for the cube rates. What's actually interesting to see is that the competition here is not as strong as for T prime equals 0. So in some sorts, the more realistic model is actually easier than the plain 2D Hubbard model. And that's in the end also good news. I mean, it's a bit more tricky from a technical point of view because we have a long-range interaction, but a more complicated model in the end does not necessarily mean that the study or that it's more challenging.
Is there a way of evaluating what would be the temperature of the experiment as compared to the energies that you see there?
I'm not sure if one could extract that directly from here, but in principle, we also start now doing finite temperature simulations.
So, but I'm saying the experiments, would they be able to have temperatures which are of the order of the gap that you see between different orders, or the temperature is much higher than that? Let's say.
Yes. So that's no, indeed, right? Sure, they can get down to this.
They can get down to this.
In condensed matter.
Yes, in condensed matter. Yeah, no, exactly. I mean, these are
how long is that kinetime called atoms experiments?
Well, they're higher. I think they started to see short-range stripe correlations in their calculations.
But how do they relate somehow?
Well, I think they start really seeing stripe physics, so modulation of the whole density. I mean, this was in a finite cell, right, with some sort of boundary conditions then. But indeed, I think it's pretty much related.
But I think in the recent period they were mostly concentrated on this dynamics of single hole or things like that. So not really on the phase diagram, but more on dynamic approach.
Yeah, right.
But it's true. They see the strange metal kind of elements.
Yeah. So another thing we observe here for this period 4 stripe is that actually superconductivity is suppressed in this case, which is not what we expected. But then we also looked at the stripe what happens to superconductivity as we vary the doping, and then we actually find 2 different regions. So there's one region at large doping where we find D-wave superconductivity, but then at low doping, if you look at the stripe, the D-wave superconductivity disappears. There is some leftover short-range pairing, but then in the triplet channel, but this seems to vanish when we go to the large D limit. So it seems that in this regime around 1/8 here, this stripe here is actually not superconducting. So if you go to larger doping, yes, but not at 1/8. Okay, but that's just, so this is, it's actually still work in the process of finalizing, so the paper should appear soon. Okay, so let me just summarize this part of my talk. So I have showed you that the doped 2D Hubbard model exhibits many low energy competing states. And with the goal of our work was to find out if stripes or uniform states are lower, and we could show that stripes have a lower energy than uniform D-wave states. Without the T prime, we found a tendency for period 8 stripes, but then with period 5 and 7 to 7 very close in energy. However, if we add a realistic T prime, we see a shift of the stripe period down to 4, which is also what is mostly seen in experiments. Now, this is not the end of the story, but rather the beginning, because now we can also move towards even more realistic models. So in principle, it's not really more difficult to also do multiband Hubbard models with iPEPS. And I think a systematic study here of different parameter sets for different cube rate families will really help to get a better understanding of all these competing phases. And for example, help to answer questions, for example, why stripes can be observed in certain families of the cube rates, but in other families they are not observed, and things like that. So I think there's really, it's a promising direction, and somehow the take-home message is that the 2D Hubbard model has become within reach for iPEP simulations, at least in the strongly correlated regime.
What about nearest neighbor interactions?
Yeah, this we can just add. Yeah, that's no problem.
Does that change the?
It does not change much. So we did not do a full systematic study. So we tried to add a nearest neighbor repulsion term, and it's in that case I think it's still period 4 stripe for realistic coupling, but it's not really much harder to do it. Yeah.
What's the computational cost now of these simulations to actually do them? How much CPU hours?
Yeah, so the 2D, the one without T prime. So these were calculations which were running of the order of maybe several weeks or so, but not really highly parallel calculations. So this was more like on the prototype level. But in the end, it's still modest CPU time that we use here. So in principle, we can really now go and scale this all up and do bigger calculations. But in the end, there's a steep increase of the computation cost with one dimension, right? So then you can go a bit further, but okay. Yes.
So how does this compare with the TJ model? So you had also some papers on the TJ model where you had 2 competing phases and they were very close in energies, and here it should be something similar.
That's right. So the problem was that back then we didn't have a good way to extrapolate these energies to the infinite D limit. And this now has also improved. So on the one hand, we can go to larger D, but on the other hand, we also can extrapolate things in a more reliable way.
So if you would do the calculation with the TJ,
it would
find something would be compatible.
I think it would be very similar, because otherwise all the physics were really very similar between TJ and Hubbard model for these values of U over T. So I think Okay, so then let's move on and switch topics. So let's go to this finite correlation length scaling. So which, as I mentioned, is an approach to study continuous quantum phase transitions, right? Which, as you know, is in general challenging to do. So here I just show you a very generic phase diagram between an ordered phase and the disordered phase, separated by a quantum critical point here, so where the order parameter vanishes. And in general, it's challenging to determine this critical point in an accurate way, and also the universal critical exponents, which describe the behavior, for example, of the order parameter in the vicinity of this quantum critical point. So G here is the relative distance to the quantum critical point. And the reason why this is challenging, from a numerical point of view, let's say, is that the correlation length diverges at the critical point. So whenever you do a simulation on a finite size system, you will always have the strong finite size effects, because the system size will act as a cutoff on this physical diverging correlation length, resulting in a phase transition which is no longer sharp, but you would see a smearing out of the order parameter around the phase transition. But the good news is that we also know what the effect of a finite system size is on quantities like the order parameter. Namely, it has a very similar effect as a finite distance to the critical point. So that we can derive a scaling ansatz, including both the distance to the critical point and the system size as a parameter. Right? So that's a typical formula for such a finite size scaling ansatz, where f is an unknown function. Now one can make use of such a finite size scaling ansatz, for example, by creating data for different system sizes and for different values of the coupling. And then by, if one chooses the right critical exponents and the right critical coupling, all this data is going to collapse on one single curve. Right? So here we plot this argument here of this function f on the x-axis, and then this we bring to the other side, and we plot this on the y-axis. And then, if you don't know this data, you can also try to find the best data collapse, and that's a way to determine these critical couplings and critical exponents. Right, so this is really a very powerful and well-established method in many fields. However, if you want to obtain this data, of course, you need an accurate method to obtain data for sufficiently large system sizes, which in general is, of course, challenging, especially if there's a sign problem. Now, our motivation was to try to do something very similar with iPEPS. Now, with iPEPS, we work in the thermodynamic limit already, so we don't have different system sizes. But the idea was to, instead of using L as a parameter, to do it as a function of an effective correlation length, which depends on the bond dimension, and then doing the finite size scaling ansatz analysis using this. Okay, so let me just point out that similar ideas and also complementary results were obtained in a paper by Michael Rader and Andreas Leuchli, which was actually published at the same time. Now, this whole idea was already developed and used in the context of matrix product states, so many years ago, and where it's also very well understood. So we know that an infinite matrix product state with a finite bond dimension can only represent states with a finite correlation length. Right? You can't represent critical states. So let's call the correlation length at the critical point psi d. So it depends on the bond dimension. And then this psi d in the end acts as a cutoff on the diverging physical correlation length in a very similar way as a finite system size. So in the end, the basic idea is to just take a finite size scaling ansatz and then replace the system size by this psi d here. Okay, so this was worked out in several previous papers. There was also an analytical derivation which links this correlation length also to the bond dimension by universal critical exponent. So here everything has been well understood. This approach has also been used in the context of 2D tensor networks for 2D classical systems, so already back in the 90s. So as you know, you can represent a 2D classical partition function as a 2D tensor network, and then you can compute thermodynamic quantities by contracting it. And the accuracy here will depend on this contraction dimension, the chi, which then also induces a finite correlation length at the critical point. And this ansatz has already been used in that context. But now, how about 2D quantum with iPEPS? Now, a priori, it's not entirely clear that this is going to work out, because unlike MPS, we know that there exist examples of critical states which can be represented with a finite bond dimension. However, all examples that have been found so far are either 2D classical states or ground states of generalized Roxar-Kibelson Hamiltonians at the critical point, which can effectively be described by a 2D CFT, right? However, if you take a Lorentz invariant critical point, so which is described by a 3D field theory, so with a dynamical critical exponent z equals 1, so time and space correlation length diverges in the same way as we approach the critical point. So in this case, there's no known example of a critical iPEPS with a finite bond dimension with a power law decay of correlations. So all simulations that have been done so far suggest also that here that a finite bond dimension induces a finite correlation length, despite that these states here actually obey an area law of the entanglement entropy. Right? So from a perspective of tensor networks, it's interesting because it would be an example of a state which has an area law, but which we cannot represent with a finite bond dimension. Now we also got some intuition why this happens here, so I will tell you in a minute. But in the end, from a practical side, it's good news because it means we can also apply here this idea of finite correlation length scaling also in 2D to study 2D critical points. Okay, so let me just briefly explain you the intuitive argument why we obtain a finite D implies a finite correlation length. So imagine we start from a state and perform an imaginary time evolution. Now I show you here everything in terms of a matrix product state, but you could also draw it for a PEPS. Right? So we have a starting state here, and then we do an imaginary time evolution step, which is encoded here by this MPO. And then after that, we truncate the bond dimension using certain projectors, which are shown here in yellow. Right? And then this gives us the time-evolved wave function at the next time step. Now, if you repeat this over and over and represent the corresponding tensor network after many, many steps, you obtain which looks something like this. So here above here, that's the ket, and down here is the bra. And then you see it's like a channel structure, right? So we have time steps, and we always do a projection afterwards. And you see on each side we have a certain 1D channel structure. Now imagine if we compute a non-equal time correlator between two different times, t0 and t1, then we contract this network here. However, we know that in a 1D setting, so this looks a bit like a matrix product state in this direction. We know that in this case, we can't get power law decaying correlations, right? So a finite D seems to imply here a finite correlation length in time direction. And because we're looking at the Lorentz invariant quantum critical point, the spatial correlations would like to scale in a similar way as the time correlations. So the PEPS tries to approximate this, meaning that the space correlation which we measure are also going to be finite. Right? So the best finite D state tries to reproduce Lorentz invariance, and somehow that's. So this is like an intuitive argument. This is no proof, but if anyone has some ideas about that, I would be very happy to discuss this later.
This argument does not also imply that in 2 dimension PEPS should have also finite correlation length. If you look at the correlation in this line, then you contract everything else. It looks like a 1-dimension system. And also one would argue that the Carnot decay is probable. However, there are examples of decay is probable.
But this is about the. Yeah, it would be interesting to discuss further, right? So, let's discuss. So we have this, and now we want to use this to do this finite correlation length scaling. There's one complication with iPEPS, that we actually have the D and also the chi from the contraction. So in principle, we would need to write down a scaling ansatz which depends both on psi D and also the psi chi. But what we do in practice here is now eliminate the chi dependence by taking the chi to infinity limit, so that the scaling ansatz we use is similar as in the MPS case, so just depending on psi D. Okay, so let me now show you benchmark results for an interacting spinless Fermi model on the honeycomb lattice. So just nearest neighbor hopping and a nearest neighbor repulsion at half filling, where it's well known that you have a phase transition between the semi-metal phase and the charge density wave phase, with a cartoon picture shown that shows the order here. The good thing about this model is that there's no sign problem, so we can actually compare with the quantum Monte Carlo data. So here I show you data for the order parameter as a function of interaction for different bond dimensions. So the order parameter is given by the difference in Fermi density on the two sublattices. And you can clearly see that we obtain a finite D effects here, right, which get weaker as we increase the bond dimension. Well, here's an example of the chi dependence at the critical point. So typically the chi dependence on the order parameter is very weak, so it's essentially converged. But for the correlation length, there's still a certain dependence on the chi, so here we have to take an extrapolation. Okay, so let's try to make use of the scaling ansatz, and the first example is at the critical point. So if G is equals to 0, then what we expect is a power law with psi d to the power of minus beta nu. So what we can do is to take our data at the critical point and make a log-log plot, and by making a linear fit, we can extract the ratio of critical exponents, which we find here is in good agreement with the quantum Monte Carlo result. Here's another example where we fix beta nu to the known value and try to find the critical coupling. So if for the right critical coupling, this quantity here is going to be a constant, right? If G is equals to 0, so it will not depend on D. So we try to find the best value for the critical coupling such that we obtain a flat curve here. And you see we obtain something which is more or less flat here for the value, which is consistent with the quantum Monte Carlo result. Okay, then we can also try to do a data collapse plot. So again, we plot this on the y-axis and the argument of this unknown function m on the x-axis. And then we try to find the best parameter sets for beta nu such that these data collapses on a single curve. Right? And then depending on the range of data points you include, you obtain slightly different values. So with a certain error bar, and what we obtain here is also in good agreement with the quantum Monte Carlo result. Now, we also thought about ways how we can determine the critical coupling directly. In conventional approaches, this is often done using a Binder cumulative approach. I don't know if you know that, but this relies on computing higher order moments of the order parameters, which is tricky to do with tensor networks. And what we did here was to try to find an alternative. And what we can do is to write down a scaling ansatz using the order parameter and its derivative. So we'll not go through the calculation. So we call it the M prime M ansatz, where you see this does no longer depend on the critical exponents. So we can take this scaling ansatz and try to do a data collapse. And then from this, we can determine the critical coupling. Right? So I think that's a useful approach in the context of tensor networks because we don't need to compute higher order moments. The last thing I would like to show you is how we can use this idea also to extrapolate order parameters for gapless systems, like for example the 2D Heisenberg model. Right? So here I show you the stagger magnetization squared of the 2D Heisenberg model as a function of 1 over psi d. And this data here can be extrapolated quite accurately to the infinite psi d limit. And it compares very well to the quantum Monte Carlo result. And that's in the end much more accurate than if you would just do a naive 1 over d extrapolation. Right? So we can also use this idea to improve estimates of order parameters in the infinity limit. Okay, so let me just summarize this part of my talk. So I've shown you this idea of finite correlation length scaling to study, systematically study quantum phase transitions. So in the end, I think it's a promising approach to study problems, critical phenomena which are out of reach by quantum Monte Carlo. Okay, so I have still a little bit of time, so just 5 minutes left. I would like to just very briefly mention two other directions. The first are SU and Hubbard models. So these are generalizations of the SU2 Hubbard model, which is I've seen before. Well, now instead of just having a sum over the two species spin up and spin down, we now consider n different species or n different colors of fermions. Right? But the model is otherwise exactly the same. And there has been increasing interest in these type of models thanks to proposals to realize them with alkaline earth atoms in optical lattices. So the idea is that you can take, for example, strontium-87 and then exploit different nuclear spin states, and then you can reach up to n different colors of fermions, right? So you can identify different nuclear spin states with these colors, and then by restricting yourself to a certain subset, you can simulate different SU and Hubbard models. Now, if you take the strong coupling limit and integer filling, then the effective model is a SUN Heisenberg model, which is given just by a permutation operator, Pij, which permutes the colors on neighboring sides. Now, both these problems are in general very challenging. So there's a sign problem, except in certain special cases. Now, iPEPS has already been very useful in this context to determine the ground state phases of these SU and Heisenberg models. And it turns out that there's really a very rich variety of different states you can obtain here, depending on the value of n and the lattice you look at. So including generalizations of valence bond solids. So these are just the cartoon pictures, or different types of color orders, or even also quantum spin liquid states. So I will not go more into the details here, so if anyone's interested, I can tell you more about this. But I would like to point out that recently we also managed to extend these calculations to the SU and Hubbard case, which is even more challenging. So in this context, we looked at the SU3 Hubbard model on the honeycomb lattice at 1/3 filling, and looked at the not insulating phases. And for large U over T, we obtained this placket phase, which is also consistent with the Heisenberg result. But as we decrease U over T, then charge fluctuations become more important, and eventually they stabilize another type of state, which is this color dimer order state with quite a large unit cell size. Okay, we'll not more go into the details, but it also shows again that these models have become within reach of iPEPS simulations, and we can really expect a rich physics here in these models. And in the end, it's also going to be useful to have predictions for these future quantum simulators for these SUN systems. Okay, and the very last thing I would like to show you our progress in doing finite temperature simulations with iPEPS. So there has been quite a lot of progress in recent years in coming up with finite temperature methods, including also recent work by Jens. And we also had a paper where we tested different imaginary time evolution algorithms, so where we worked with a purification of the thermal density matrix. And I think on the application level, we also have reached an interesting level where we can address those problems which are out of reach by quantum Monte Carlo simulations. So in the ongoing work, we're looking at the so-called Shastri-Sutherland model. So that's a spin 1/2 model on this particular lattice here, which has a very nice realization in the material, in the strontium copper borate. So also iPEPS was also useful in this context previously to study the ground state phases of this material. And what I'd like to show you here is just a few examples of the specific heat obtained with iPEPS. So for a coupling ratio of 0.5, Quantum Monte Carlo does not have a bad sign problem, so we can actually compare. We get a good agreement with Quantum Monte Carlo. If you go to coupling ratio 0.6, where we get closer to the actual value of the material, we see that Quantum Monte Carlo starts having a very strong sign problem, so we can't really access anymore the low temperature behavior here. And then in the end here, just show you a comparison of the experimental data and iPEPS, where we obtain a very nice agreement at low temperature. At low temperatures, things start to deviate at high temperatures. However, this is supposed to be because the spin Folman couplings have not been included here. Okay, so in the end, these are just a few results which are going to appear in a paper soon, where we also compare the data obtained with different methods obtained by my collaborators. Okay, so in the end, I think it looks promising that we can actually really use 2D tensor networks to address challenging problems, also in 2 dimensions at finite temperature. Okay, and with this, I would like to summarize. So I guess everyone agrees that 1D tensor networks have been the state of the art for many decades. 2-dimensional tensor networks are more challenging, but there has really been a lot of progress in recent years. I think iPEPS and PEPS have really become very powerful tools to study challenging problems, right? So I showed you just a couple of examples today, but of course there's many more examples here. So, and I think what's also important to emphasize is that there's really still big room for improvement. So we can really still further improve the optimization and contraction methods, so that we can also expect a higher accuracy in future. And many groups work on interesting extensions, like the computation of excitations or open systems, 3D systems, and so on, right? So there's really a lot of things happening. And I also find it very interesting that tensor networks are getting more and more important also in other fields, right? As we see here at this workshop. So I think it's really a very exciting time to work on these tensor networks. And with this, I would like to thank you for your attention.
When you talk about a kind of strong sign problem in quantum Monte Carlo, you seem to imply that there's also a kind of a weak sign problem of the sort, and there's known relations between the strength of the sign problem or the average sign with most of sample complexity, how much overhead you need to get a certain accuracy in your description. Mm-hmm. Is that something you see kind of in practice, that if there's a little bit of a sign problem, you kind of get away with it? And yes, it becomes worse when it's worse. It's something that you encounter in practice. I mean, you know the theory side, but not.
But it's actually amazing that there's really a revival of doing quantum Monte Carlo simulations also for 2D Hubbard models. Because in the end, you know, with the computer power that you nowadays have, I mean, it's exponentially hard, but it doesn't mean you can't do it, right? If you run it enough, you can get, and you might still reach interesting temperatures. So actually, there's more and more, again, there's a revival of the quantum Monte Carlo, even if there's a sign problem. Because it doesn't mean that you can't do it, right?
So you get, like, of course, asymptotic is exponential, but with a very slow slope, then if you get a little sign problem.
That's right, yes. So it depends on the region, and people are also working, you know, trying to make it weaker, the sign problem, by doing some basic changes and so on. So actually also here, this, if you just take the plane, the normal, the usual basis here, you could not do this with Monte Carlo. So this was actually already quite an achievement to find another basis in which you can do quantum Monte Carlo here for this coupling value. So that was another work that was also involved. But in the end, unfortunately, it was still too strong that if you go to the coupling values relevant for the material, that you could get out something. But so the quantum Monte Carlo people here were already very much amazed that they can do that. Yeah.
So what do you see as prospects for gate series projects?
So I never tried myself, but I think yes, I did think that this is going to be. To me, it looks very promising, and it's also a matter of pushing these calculations to become competitive. Right? If you look from other communities using other approaches, often these are really large scale high performance computations, right? And we're still not doing that on the tensor network level. So I think there's so much room to improve things. So I think it looks really. I think I'm optimistic. Yes, but I'm not trying to say.
So you have mentioned several times that in fact originally these problems have been developed for classical team models by Rodney Baxter and Nishina, and to calculate the partition function. But in principle also, I understand that they can be also applied to classical stochastic many-body dynamics, like kinetic easing models or exclusion or this diffusion aggregation problems. I think Frank was once working on something like that. Is there any progress in this kind of area? Is there something that we should know? Do you know?
I don't know too much about this, so I can't really tell.
Because it's another area.
It's another area.
Not trivial if you think about, I don't know, dynamic of the easing spin glass, classical. And
That's right.
This is a very challenging problem. And in principle, you can apply again.
Yeah, it would be interesting. Exactly, it would be interesting to see how far it can go, but I don't know. I don't have experience.
So there are no other questions. Let's thank Philippe.
Great. Very impressed.
Okay, thank you. Yes. You have to leave. So that is too bad because it would have been interesting to talk about the other thing. To me,